Hey everyone, in this video we're going to learn how to scale and reflect parent functions. Scaling can be broken down into horizontal scaling and vertical scaling, and then we have two types of reflections that we're going to look at. We'll start with vertical scaling, which is multiplying the y-coordinate of each point on the graph of a function by a constant. So in order to understand this, let's compare the graphs of y equals x squared and y equals 2x squared. So in red, we have the graph of our parent function, y equals x squared, and in blue, we have the graph of y equals 2x squared. So we're thinking vertically, so I want our focus to be up and down the y-axis. So for instance, if I take a point 1, 1 on the parent function, I'm going to compare it to the point above it at 1, 2. So if I'm looking at this and asked what happened to the red graph that got me to the blue graph, well, intuitively, my first answer might be, it was moved up 1. I took the point 1, 1, I moved it up to the point 1, 2. Now that rule should be true for any point on the parent function. Well, if I look at the vertex 0, 0, to get to the blue graph, it wasn't moved at all. It wasn't moved up 1. So my first thought is incorrect. I need to go back to the drawing board. So now back to that point 1, 1, comparing it to the point 1, 2. Well, if I take the y-coordinate of 1, 1 and multiplied it by 2, I would get the point 1, 2. So let's take that idea now. So I have 0, 0 as the vertex. I multiply the y-coordinate by 2, I get 0, 0 still. Okay. Let's take another point. 2, 4. Multiply the y-coordinate by 2, I would get 2, 8. Which is the point right above that on the blue graph. So it seems that we figured out what our scale factor is. To get from the parent function to y equals 2x squared, we have to multiply the y-coordinate by 2. Now let's look at the table of values. It may be even more clear when we have a table of values. We notice that the x values are the same, and the y values of the parent function, in comparison to the y values of y equals 2x squared, well, if we take these y values and we multiply by 2, we would get the y values here. So 2 is our scale factor. So for any x value, what do we multiply the y-coordinate of y equals x squared by to get the y-coordinate for y equals 2x squared? We figured out that's a scale factor of 2. If we were asked to describe the graph, I would say that y equals 2x squared is narrower than the parent function, and we classify this mathematically as a vertical stretch. And we'll formally define this in a later slide. Okay, but essentially we took the parent function and we stretched it upwards. Let's look at another. So we have y equals x squared compared to y equals 1/2 x squared. So the parent function is in red. Again, we're looking vertically, so I only want our focus to be up and down. So let's take the point 2, 4 and compare it to the point right below it at 2, 2. Again, my first instinct might be I moved it down 2. But as we compare, we can see that that's not true for every point. So now, how do I get 2, 4 to become 2, 2? Well, if we multiply the y value by 1/2, then I would accomplish that. Let's see here. 1, 1, if I multiplied by 1/2, I would get 1, 1/2. 0, 0, that stays 0, 0. Comparing the table of values, well, we can see that if we multiply the y values by 1/2, we would get the y values in y equals 1/2 x squared. Notice the x values are exactly the same. The only thing that's changing is the y values. So we have our scale factor. In this case, it's 1/2. So for any x value, what do we multiply by? We multiply by a factor of 1/2. How would we describe the green graph, y equals 1/2 x squared, compared to the parent function? Well, vertically, it looks like the graph has been compressed. It's been pulled closer to the x-axis. We can also refer to this as a vertical shrink. So there's our vertical scaling. We saw one where we're scaling by 2, one where we're scaling by 1/2. Now we have to look at the horizontal scaling, which is multiplying the x-coordinate of each point on the graph of a function by a constant. And we're going to compare y equals x squared and y equals quantity 2x squared. So in red we have our parent function. In pink we have the graph of y equals quantity 2x squared. So let's, again, now we're working horizontally, so I want our focus to only be left and right, only horizontal. So if I have the point 2, 4, I'm comparing it to the point to its left at 1, 4. We can, again, maybe think that it was moved to the left 1, but we could see that that's not true for every point on the parent function. So how did we get from 2, 4 to 1, 4? Well, we can multiply the x value by a half. 2 times a half would be 1, and the y value stays the same. Take 1, 1. Multiply the x by 1/2, I'd have the point 1/2, 1. 0, 0, that's going to stay 0, 0. Now to emphasize this scale factor, I changed the table of values for y equals x squared. We wouldn't normally use this table of values because we can't plot 16 on a normal axis that we're given, but these are all still points on y equals x squared. We have negative 4, 16, negative 2, 4, 0, 0, 2, 4, 4, 16. So in comparison, we can see that the y values are exactly the same. Now compare their x values. Well, if we took the x values here and multiplied by 1/2, we would get the x values in y equals quantity 2x squared. So our scale factor is 1/2. So now we've changed the question for any y value, because the y values stay the same. What do we multiply the x coordinate by? Well, we multiply it by 1/2. And if we were comparing our graph, we would say that y equals quantity 2x squared is more narrow. So that means horizontally, if we were looking left and right, it was compressed horizontally. It's like we put our hands on the parent function and we squeezed in. Okay? So horizontal compression. And then lastly, we have y equals x squared and y equals x divided by 2 quantity squared. We can see the graphs here. So again, we're working left to right. So if I'm comparing 1, 1, its point to the right is 2, 1. So how did I get from the point 1, 1 to the point 2, 1? Y values are the same, x values are different. I can multiply the x by 2. I have the point 2, 4. If I multiply x by 2, I would get 4, 4. The vertex at 0, 0, multiply x by 2, it's still 0, 0. So if we look at the table of values, to really solidify this idea, y values are all the same. The x values, if we multiply by 2, we get the x values here. So for any y value, what do we multiply the x coordinate by? What's our scale factor? Well, it's by 2. And if we were comparing our graph, I would say that the graph became wider. And horizontally, it's like we took y equals x squared and we pulled it out left and right. Okay, so we would say that we stretched it out horizontally, a horizontal stretch. Okay, so individually, we now have our 4 different types of scaling. Algebraically, how do we figure out that that's the case? Well, let's now look at them a little bit more carefully. We have x divided by 2, and that's being squared. So the divided by 2 happened inside the parent function. We had 2x, and that was being squared. So the 2 was inside the parent function. And in both of those cases, we had a horizontal scaling going on. And then if we look at our vertical, we have 1/2 x squared. So the 1/2's not in parentheses now. We do the x squared, and then we multiply by a half. Similar for y equals 2x squared. We do the x squared, and then multiply by 2. And those were both vertical scaling. So it seems if it's happening outside of the parent function, it's a vertical scaling. And if it's happening inside the parent function, it's a horizontal scaling. So let's formalize this idea. In order to determine the scaling of a function, rewrite the function in the following form. Y divided by b equals f of x divided by a. Now I know that seems weird. We normally like our equations in y equals form. But by rewriting it this way, we now can stay consistent with how we think of our scale factors. And I think when we put numbers here, it will make even more sense. whatever is happening to the x value, so inside the parent function, that's our horizontal scaling. So a is our horizontal scaling. And then whatever's happening to y over here on the other side of the equation, that represents our vertical scaling, because our y values are vertical, x values are horizontal. Now, to classify the words that I was using, if a is greater than 1, we classify the scaling as a horizontal stretch. Right, so if we're multiplying every x value by 2, like we were, it would look like we're stretching it horizontally, left to right. If a is between 0 and 1, then it's going to look like we're compressing it horizontally, and that graph's going to become more narrow. For the vertical, if b is greater than 1, then it's going to look like we stretched it vertically. And if b is between 0 and 1, it's going to look like we compressed it vertically. Okay, so a lot of new vocab here, but as we get graphs and as we write equations, it's going to become more familiar to us, and we're going to get a better understanding. Now, what happens if it's negative? We never talked about that yet. So what happens if a is negative? Okay, so here we have y equals the square root of x, and y equals the square root of negative x, which if I write in the form from that last slide, it would be y equals the square root of x divided by negative 1. Okay, so it's happening to the x values, the scale factor. So we're going to multiply each x value by negative 1. Right, so times negative 1, we get the x values here. Well, how does that look graphically? Well, it looks like I took the parent function and I reflected it over the y-axis. So that's exactly what's going to happen if a is negative. We're going to classify that as a reflection over the y-axis. Okay, so if our horizontal scaling is negative, on top of being either a horizontal stretch or a horizontal compression, we also have a reflection over the y-axis. And then what about b? Well, if b is negative, so here we could see negative square root of x, which if we rewrite it like that previous slide, it'd be y divided by negative 1 over the square root of x. So looking here, it's telling me that I should multiply my y values by negative 1. Y values times negative 1 would give me exactly these y values. And what does that look like graphically? Well, it looks like I reflected the parent function over the x-axis now. Right, and think about this intuitively. If you have a bunch of points and you make their y values negative, well, the point 1, 1 would go to 1, negative 1. Right, and that would consistently happen. X values don't change. The y values are going to go from above the x-axis to below. It's going to look like a reflection. Okay, so now we have everything classified. We have our scaling and we have our reflection. The one thing I want to touch upon before we go too far is why in the equation, if I'm dividing by negative 1, in the table of values, it looks like I'm multiplying by negative 1. And the reason for this is the equation always tells us how to get back to the parent function. It's telling us you have the graph of y equals negative square root of x. If you want the graph of the parent function, take the graph you have and divide it by negative 1. Now that's really helpful if this is the graph that we start with, but typically we're going to start with the parent function because that's the one we know. So they're trying to be helpful, saying, hey, if you have this, divide by negative 1 and you get this. So we have to reverse that idea to go from this, which is what we know, one of our parent functions that we know, to get to the graph that we really want. And it'll take a few examples to wrap your head around that idea, but if you do, that makes transformations that much easier. The equation's trying to tell you to get back to the parent function, so reverse it in the way we think. So determine how each function has been scaled or reflected in comparison to its parent function. So we have y equals 5x cubed. So the first thing is let's rewrite it. Even if it looks weird, let's rewrite it. So the 5 is not inside the parent function, so I'm going to write this as y divided by 5 equals x cubed. And if I want, I can even write this as x divided by 1, if that's helpful. So our parent function here is y equals x cubed. So how has this been scaled or reflected? Well, in the equation, y is being divided by 5, x is being divided by 1. So we're going to multiply the x's by 1s, so that doesn't change anything. And we're going to multiply the y's by 5. Now, I have a shorthand notation for this, so it's a scaling 1, 5. So what this means is multiply the x, so that scaling is x, y. What we're doing to the x's, what we're doing to the y's. And actually, let me even stay consistent with the notes. Scaling of a, b. What we're doing to the x's, what we're doing to the y's. Now, it's really helpful, this notation, but we also have to know how to write it out. So we would classify this as a vertical, stretch or shrink. We're making the y values larger, so it's going to look like the graph is getting narrower. So that's a vertical stretch by a factor of 5. And this is our answer. This scaling shorthand notation is going to be helpful when we're creating a graph. Okay, let's look at our next example. Y equals the absolute value of x divided by 6. So it's already written in that form for us. We don't have to do anything. So what would the scaling be? Well, x is going to be multiplied by 6, right? Because the equation is saying divide by 6 to get back to the parent function. So multiply by 6 to go forwards. And then we could write y divided by 1. So we're just multiplying y by 1. It remains unchanged. We can't write 0 because remember, if you multiply everything by 0, then it becomes 0, and we have that becomes a problem. Okay, so how would I write this out? Well, multiplying the x values means I have a horizontal scaling. I'm multiplying them by 6. So if I took each value, x value, multiply by 6, they're going to move out left and right. So that's going to be a horizontal stretch by a factor of 6. Okay, so hopefully we're starting to get the hang of this. Let's look at our next example. So we have y equals negative 3 over 2 times the cube root of x. So let's rewrite this. So it's y divided by negative 3 halves equals the cube root of x divided by 1. I know we don't normally like to divide by a fraction. Some of us intuitively would have written 2y over 3, but try to avoid that here. I want that y by itself in the numerator to figure out the scale factor. So our scale factor here, x we're multiplying by 1, y we're multiplying by negative 3 over 2. So right off the bat, I see that scaling is negative. I know not only is there a scaling, there's also a reflection. Now we got to use words. We got to write it out. Okay, so we're multiplying the y, so that's a vertical stretch. And I know it's a stretch because 3 over 2 is greater than 1. I'm making the y values bigger. So vertical stretch by a factor of 3 over 2. And then what's the negative doing? Well, if I negate the y values, that's going to be a reflection. Negate the y values. Okay, think about this intuitively. I negate the y values. They're going to go from above the x-axis to below, or from below to above. So I'm reflection over the x-axis. Okay, so this actually had two pieces to it. Our scale notation allowed us to just write it once, which is going to be really convenient when we're graphing. But identifying, we have two things to identify here. And then next, we have y equals f of negative 4x. Okay, so I want to rewrite this as y equals, so y over 1, because there's nothing in front of the f of x divided by negative 1/4. So take a second to wrap your head around this. If I divide by negative 1/4, it's the same as negative 4x. But again, I want that x by itself in the numerator so I can identify my scale factor. The f here, not meant to throw us off. They're just trying to generalize the idea of a parent function. Okay, so what do we got? We have a scaling. We're multiplying the x values by negative 1/4. Right? The equation is telling us to divide to get back to the parent function. So to go forwards, we're multiplying. And we're going to multiply the y values by 1. Okay, so that means Not only do I have a horizontal scaling, I also have a reflection going on. Okay, so I have a horizontal what? Okay, well, I'm multiplying by 1/4, so I'm making the x value smaller. So it's going to be a horizontal compression. Or a shrink. We can use those words interchangeably. By a factor of 1/4. And then what's that negative doing? Well, if I negate the x values, that means I'm going from one side of the y-axis to the other. Okay, so reflection over the y-axis. Okay, so two things going on. As long as we can rewrite it here, we can identify each piece. Last two examples. So y equals 7/3 times the quantity 6x squared. So now we have both things happening at once. So let's rewrite this. So we're going to write it as y divided by 7/3 equals, okay, 6x. I'm going to write it as x divided by 1/6 quantity squared. And I know it looks super weird, but from here I can say the scale factor. Well, if I'm dividing x by 1/6 in the equation, that means I'm multiplying by 1/6 to get the graph. And then I'm going to multiply the y's by 7/3. Okay, so describe what's happening. We have a horizontal compression by a factor of 1/6 and a vertical, let's see, 7/3, that's going to make the y values bigger, so vertical stretch by a factor of 7/3. And I understand, why can't we just leave it here? So much easier, less writing. I hear all those arguments. But this really explains that you know what you're talking about. Last one. Y equals -9 times f of x divided by 5. So we have y divided by -9 equals f over f of x divided by 5. So our scaling, in the equation we're dividing x by 5, so we're multiplying x by 5. Dividing y by -9 means we're multiplying by -9. So here we have three things going on: horizontal, vertical, and a reflection. Okay, so we have a horizontal stretch by a factor of 5, a vertical stretch by a factor of 9, and then a reflection. Well, what type of reflection? We're taking the y values, we're making them negative, so we're going from one side of the x-axis to the other. So reflection over the x-axis. Okay, so there was a lot happening. So my first piece of advice would be to go back and watch any piece of this video that still doesn't quite make sense. Okay, the second piece is rewrite your equation. It might look really weird. It's not something we normally do. But by doing this, we can get the equation into a form that we're staying consistent, right? The same way we think about x's, we think about y's, which is really nice. And the equation always tells us how to get back to the parent function, which is not what we want. We want to go from the parent function forwards. So we have to reverse everything. And then make sure we know how to tie the numbers, the values, to what they actually mean. Multiplying an x value by 5, that is a horizontal stretch. Multiplying a y value by 1/3, that is a vertical compression or a vertical shrink. So the only way to do that is to get a bunch of practice in. So do that before transitioning into the next video. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.